So let's build on what we know about molar mass and talk about stoichiometry and limiting reagents. So the goal of stoichiometry is to use the mass or moles of one reactant or product we're given this information to find the same information or mass or moles of another reactant or product. And really, to make this as simple as we can use a sample reaction to demonstrate how this is useful. Okay, so we've got this reaction with reactants A and B. The balanced coefficients, lowercase a and lowercase b, yield products C and D with their reaction coefficients as well. So let's say that we're given the amount of reactant B and we are looking for product D. Okay, so we would start with grams of B, and we would want to get rid of grams to convert to moles. Okay, so when that happens, we use the molar mass as our first conversion factor. Okay, and then we want to get rid of moles of B, so it goes on bottom again. Again, we've canceled grams and now we're at moles, and what compares but the mole ratio of moles of D to moles of B. And so to get that mole ratio, we put in the constants out front. Okay, so the coefficients of the equation here are going to give us the mole ratio. So we've got the molar mass, and then the mole ratio is next. And we then say, well, I don't want moles of product, I was asked for grams of product. And so then I say, well, I want to get rid of moles of D and I want to get grams of D. Well, this is just the molar mass derived from the sum of the atomic weights on the periodic table. Okay, so it's just a different molar mass. And using dimensional analysis here, once I've canceled moles of D, I end up with, once I multiply everything together, some grams of D. So I'm going to work through this process. I can start anywhere I like. Okay, I can start using A, I can start using C, but as long as I do the cancellations that are driven by me canceling out, by putting on the bottom the next unit to cancel out the given unit and get the new unit, I'll be in good shape. Okay, so it's the same way every time, and the best way to learn it is to do examples. So let's look at a couple of rules that we must follow to get these problems correct and to get useful information. We must start with a balanced equation. Okay, this is a must. We have to have the equation balanced to be able to use the mole ratio. We can compare moles to moles of two different compounds from the coefficients of the balanced equation. These are the mole ratios. And from our equation above, they might be C, lowercase c, moles of C to the coefficient on D and so forth, or we can flip it around and use whatever we like. We can compare moles to moles. We can compare the coefficients. What we can also compare is grams to mole of a single substance. So we can say grams of A per mole of A. Okay, this is the molar mass, mole of A to grams of A. Or I can change A to B. What I cannot do is say moles of C to grams of B or something like that. Okay, I have to have the same substance. I can compare grams to moles. That's the molar mass. What I cannot do, I cannot compare grams to grams of two different substances. So I cannot say 5 grams of A to 10 grams of B. That is not something I'm allowed to do. All right, cannot do it. And I can also not add the masses of reactants to get the theoretical yield. You must consider the limiting reagent. So if I'm given 5 grams of A and 6 grams of B, that does not mean I'm going to get 11 grams of product. Okay, that does not happen. We have to know which reagent is limiting. That is illegal for us to do. We have to solve it using stoichiometry. And so if we know that we have a limiting reagent, we know what that limiting reagent is, we only have to solve once. Okay, so we only have to solve it once using the data for the limiting reagent, or if we've got exactly enough, we can use either one. If we don't know, and we're given the masses and moles of multiple reagents, we have to solve once for every reagent and then pick the lowest yield as the theoretical yield. So that's a lot of words, but the best approach to learning stoichiometry is to do examples. For example, ethane is completely combusted in air in 2 experiments. In the first experiment, which I've briefly outlined here to save time, I've written an equation that takes the word problem and turns it into an equation that we have to balance. Okay, and so in order to balance this reaction, I've got an odd number of carbon or oxygens on the right, an even number on the left. So the first thing I've got to do is to make that even. And when I do, I notice that the next complicated reactant, the most complicated reactant, ethane, has 6 hydrogens and 4 on the right. So that means I've got a problem where I need to get the least common multiple, which is 12. Okay, so 6 times 2 is 12. Then 2 times 6 is 12. And that leaves me with 4 carbons, so I can fix that here. And that gives me 8 oxygens plus 6 is 14, so I need 7 oxygen molecules to balance out to 14 oxygens on the left and the right. Okay, so quick balance the equation, first thing on every one of these, and then I've diagrammed 3 sets of informations or of information in this column. Okay, so grams, we need grams. We're given 10 grams of ethane, and with moles we have to solve for, but molar mass is something that we can calculate in each problem directly from the periodic table, which will be given. And so if we add up all the atomic masses, we get 54.09 grams per mole for ethane, 32 for oxygen, 44.01 for CO2, and then 18.03 for water. And so what do we want? Well, we're given 10 grams, we want grams of CO2. And to get there, we've got to go through moles because we can't compare grams to grams. And then we can compare moles to moles using the mole ratio. Then we can get back to grams using the molar mass. And so whenever we have a problem in stoichiometry or any chemistry or physics problem, start with your given. And then whatever unit you're given, let's cancel it out in the next conversion factor by putting it on the bottom. So what compares grams to moles? We want to get moles. We want to get rid of grams. That's the molar mass, which we've already prepared for ourselves. We've already gotten that information ready to go, so we're in good shape. 1 mole is 54.09 grams. Cancellation. Then we want to get rid of our next unit. So we want to get rid of moles of C2H6, and we go to the balanced equation. So to get moles of CO2, the balanced equation says 4 moles per 2 moles of ethane. And we can get rid of the mole units, the moles of ethane units. What do we want to get rid of now? Our last conversion factor, moles of CO2 to grams of CO2. We have the molar mass, and so then we say 44.01, and we divide and multiply out, and we get a theoretical yield of 16.3. If rounded to 2 significant figures, we would say just 16 grams of CO2. Does that seem reasonable? Starting with 10 grams of ethane, and 4:2 mole ratio is going to be greater, so yes, it does seem reasonable. So if two sets of reaction data are given to us, and we don't know which one's the limiting reagent, we have to perform the calculation twice. So what are we given? We're given 10 grams of ethane. We are given 5 grams of oxygen, and we want grams of CO2. So we're not concerned about water. We can get rid of those and not concern ourselves with the information for water. And so we've already calculated through this route for 10 grams of C2H6 of ethane before, and that gives us a value of 16.3. But we also have to calculate to 3 significant figures what happens if 5 grams of oxygen is the limiting reagent. So we start with our given. As always, get rid of the given units. We want to get to moles via this path. Okay, so let's convert to moles. And 32.00 grams per mole is the molar mass. Then we want to get rid of moles of O2 and get moles of CO2, just like we did before, just have to do double the work for limiting reagent. And 4 moles of CO2 and 7 moles of O2 from the balanced equation gives us the mole ratio. And again, we've canceled those units. Now we want to get rid of moles of CO2 and get 2 grams of CO2. And that's the molar mass. So now we want to multiply everything out into 3 significant figures. We have 3.93. And so because 3.93 is less than 16.3, the 3.93 is the theoretical yield for CO2. Okay? Because we have to take the lesser of the two, 16.3 versus 3.93. Oxygen limits the amount of carbon dioxide we can produce by this reaction to 3.93.